The current American program to return to the moon, it's called Artemis, has 3 planned missions. The first was an uncrewed mission to the moon. It went to the moon and came back, splashed down in the ocean. Good. Second is a crewed mission to the moon, but not land yet. Third would be a crewed mission to the moon where you land, right? Incremental steps, just as Apollo had unfolded. That's one of the reasons why there were many Apollo missions. Each one was incrementally more ambitious than the previous one. So, this is how space works. If you want to stay safe in the process, especially when it involves people, crew, astronauts, and look forward to seeing what comes of that. Good luck, SpaceX. Godspeed to you.
These gentlemen are discussing how you don't leap to the finish line in space flight. You build up to it. That's not caution for its own sake. It's respect for the reality that rockets, crews, and the environments they traverse are governed by physics that do not care about our schedules. When you see a program staged in steps, first without people, then with people, but no landing, then a landing, that's not bureaucracy. It's an evidence ladder. Each rung answers a question you can't answer from a conference room or a computer model. Consider how we learned this the hard way. Early in the Apollo era, a cabin fire on the pad forced a complete rethinking of materials, wiring, and procedures. Later, a mission looped around the moon months earlier than planned, because the safest way to test the spacecraft's deepest abilities was to actually go deep. Another flight rehearsed the landing without touching down, just to make sure the rendezvous and descent systems did what the textbooks promised. Progress wasn't linear, it was conditional. If this works, then attempt that. If it doesn't, diagnose, redesign, and try again. Here's the part we rarely admit. A successful, uncrewed mission isn't proof of success. It's an invitation to find subtler failures. When a capsule returns from deep space, engineers study heat shield char patterns millimeter by millimeter. Did the ablation match our models? Did it shed material in ways we didn't predict? Lunar return speeds push your thermal protection to its limits. Re-entry corridors just a few degrees wide decide whether you skip off the atmosphere or come in too steep. A test that looks like a victory parade might, under a microscope, reveal a problem that would have put a crew at risk. That's why the second step isn't just the same thing with people. It's a different mission designed to stress different parts of the system while preserving a margin for abort. And that margin is not just a seatbelt. It's a chain of lifelines, launch escape systems, redundant avionics, backup power, comm links that can ride out radio blackouts. The deeper you go from Earth's cradle, the weaker your safety net becomes. Outside the magnetosphere, radiation is not an abstract hazard. It's a real-time operational constraint. Galactic cosmic rays erode electronics in your DNA. Solar particle events can deliver dangerous doses in hours. The Apollo era was lucky. One major storm occurred between 2 missions. Luck is not a plan. Modern missions carry better forecasting, vest-like shielding, and storm shelter procedures. But the only way to trust your protocols is to test them in authentic conditions, at durations long enough to matter. Now, add the moon itself. Lunar dust isn't dirt. It's glassy, jagged debris that clings electrostatically and abrades seals and joints. It fouled suits in the 1960s. It can still compromise mechanisms today. Hazard detection LiDAR and terrain relative navigation can pick safer landing sites, but those algorithms must be verified over real landscapes from real altitudes. That's another rung on the ladder. Test vision systems and lunar lighting, where the sun is relentless and shadows are ink black. You don't want to discover glare problems with a crew watching the surface rush up. There's another catch. To land people sustainably, you need more than a lander. You need logistics. Refueling in orbit asks you to master cryogenic propellant transfer without boiling away your cargo. That means depots, insulation, sunshades, and docking choreography repeated over and over. The rocket equation doesn't negotiate. If you want a large lander to reach the moon, you either launch it in pieces and refuel, or you accept a tiny payload. These are not managerial preferences. They're consequences of exponential math. So, the path forward includes a sequence of flights that look repetitive. Tanker after tanker, test after test. To the impatient, it looks like dithering. To an engineer, it's how you turn a PowerPoint arrow into an interplanetary highway. Cliffhanger time. What if we could bypass all that with robots? We did, and we will. Robots go first, take the risks, scout landing zones, map resources like water ice and shadowed craters. But robots and humans are not interchangeable. People improvise, they repair, they notice the unexpected context, how dust floats in a hatch, how a drill behaves in powder, how your body handles a week of fractional gravity. Human presence is a sensor suite evolution spent millions of years building. And when the mission is to build something enduring, a communications relay, a laboratory, a power grid, hands, eyes, and judgment accelerate everything. The responsible move is to let robots reduce uncertainty, and then let people capitalize on what robots reveal. If all this sounds like we're trying to make the moon boring before we make it normal, exactly. Aviation got safe when airlines stopped trying to impress and started living by checklists and procedures. And the path to routine in space is paved with disciplined repetition and a ruthless feedback loop. Test, measure, learn, iterate. Commercial partners live by this too. Even if their public persona celebrates rapid iteration, you can fly prototypes fast and often when they're empty. But when you add a cockpit with names and families, the tempo shifts. You adopt conservative design margins and accept that the calendar is secondary to the data. There's a reason we're returning to the moon before going to Mars that goes beyond nostalgia. The moon is a nearby laboratory that mirrors many of the hard problems we must solve for Mars. Deep space radiation, abrasive dust, brutal thermal swings, partial gravity surface work, and learning to live off local resources, while not reproducing Mars-specific hurdles such as minutes-long communication delays or the challenge of entering, descending, and landing through an atmosphere. But it's 3 days away, not 6 months. If a system fails, you can abort and come home. You can build a small gateway station and practice deep space operations without the full commitment of a Mars transfer. You can learn how to close life support loops more tightly, how to recycle water and air, how to manage power cycles through long lunar nights, how to print parts from local regolith. Each success buys down risk for the next frontier. So, when you see a lunar program unfold in careful tiers, rate it not as timidity, but as strategy. The hero of the story isn't the moment of landing, it's the scaffolding that makes landing repeatable. Our ambition should be audacious in scope and meticulous in method. The takeaway is simple. In exploration, courage is not the opposite of patience. Courage is aligning your urgency with the evidence and letting reality, tested, measured reality, set the pace. That's how you plant footprints that lead somewhere, rather than stampede toward a place you're not yet ready to inhabit. Like if this was interesting, and hit the subscribe for more.